Hello there, and welcome to Just About Earth, where curiosity gets cosy and science takes its time. Whether you're winding down for the night or just letting your mind wander a little before sleep, I'm glad you're here. Tonight, let's follow a question. Not one with easy answers or neat edges, but one that invites us to think differently about the ground beneath us. What if Earth was designed? Now, I don't mean designed as in picked off a shelf or assembled like a flat-pack bookshelf, although the idea of tiny cosmic tools is admittedly fun to imagine. I mean the broader idea. What if Earth wasn't just the result of random events and blind physics, but something shaped, intentionally, methodically, by some force or process? Whether you picture that as an intelligent creator, a complex simulation, a vast natural algorithm, or something else entirely is up to you. The point is, we're going to explore this not as a debate, but as an exploration. No loud opinions here, just quiet questions. And we won't be rushing to answers. That's not the pace we keep around here. Instead, we'll take a slow walk through the landscape of the idea, noticing the small details and the big patterns. And maybe along the way we'll discover that even asking the question opens new ways of seeing the world, ways that are just as important as the answer, if not more. To begin, let's start small. Not with physics or philosophy, but with the simple personal experience of looking around. Think about your ordinary day. You wake up to light pouring through your window, not too hot, not too cold. You breathe in air that your body is perfectly built to use. You get thirsty, and water, clear, tasteless, essential, is there, waiting. Maybe you go outside. Plants, animals, sky, temperature, gravity. Everything seems to line up in just the right way to make life not only possible but comfortable. It's easy to take that for granted. Most of us do. But under that comfort is something worth pausing over. Is it all coincidence? Could it be? Or is it arranged, like pieces in a puzzle that just happen to fit a little too well? Of course, science has offered a detailed, well-evidenced story of how Earth came to be the way it is. There's no shortage of information on the early solar system, planetary formation, chemical evolution, and so on. We've built models, gathered data, and traced timelines that stretch billions of years. It's a robust framework, and yet, even within that framework, there are things that make people pause, things that seem, frankly, a bit too convenient. Earth orbits a very stable star. It does so in a range that's often referred to as the habitable zone, a zone where water can exist in liquid form, which turns out to be pretty important for life as we know it. That alone might seem fortunate, but it goes further. The planet's tilt, which gives us seasons, its rotation speed, which keeps temperatures from swinging wildly, the size of the moon, which affects tides and stabilizes that tilt, the presence of a magnetic field that shields us from solar radiation, the mix of gases in the atmosphere, the balance of land and ocean. You can keep going. Each of these things could have been different. Wildly different. And if they were, life as we know it might never have appeared. Some call this the anthropic principle, the idea that, of course, the universe looks suited to life, because we're here to observe it. If it weren't suited to life, we wouldn't be around to ask these questions in the first place. It's a tidy explanation in one sense, but it doesn't stop the wondering. Is it really enough to just say, well, we're here, so it must have worked out somehow? Or is that dodging something deeper? Now, none of this proves design. That's important to say. Patterns don't prove purpose, but they can point to it, or at least make it worth considering. So what we're going to do is look at these patterns, not as believers or skeptics, but as explorers. We'll wander through the clues and coincidences, the physics and the philosophy, the math and the metaphors, and we'll do it slowly without needing to land on a single conclusion. Because whether Earth was designed or not, it behaves in ways that often feel as if it was. That's not a claim, it's just an observation. An invitation, really, to ask, what would be different if it were designed? What would stay the same? To explore this, we'll need to go wide and deep. We'll talk about planetary physics, of course, and biology and chemistry. But we'll also talk about perception and narrative, and why humans are so drawn to the idea of a world made with intention. Some of that might come from religion, sure, but not all of it. The urge to look at the sky and feel that it means something is older than any book or temple. It might be something built into us. Take, for example, the way we interact with symmetry. We're drawn to it. Faces, flowers, shells, galaxies. When we see symmetry, our brains light up. It feels right. That preference isn't proof of anything, but it's a starting point. Why should a universe formed by randomness keep giving us order? Why does our sense of beauty so often align with what turns out to be efficient, functional, and mathematically elegant? This is where things get interesting, because even if you start from a purely scientific worldview, you still end up swimming in questions that sound philosophical. The more we learn about biology, for instance, the more we realise how incredibly fine-tuned many systems are. From the way proteins fold, to how DNA stores information, to the way cells communicate, it's all precise, interdependent, and in many cases, inexplicably efficient. Not perfect, certainly. Evolution is messy, and the body is full of quirks and leftovers, but it works astonishingly well, and it works in ways that sometimes resemble what we might call design. Now, design is a loaded word. It tends to bring up images of a conscious being sketching blueprints or tweaking molecules. But it doesn't have to mean that. It can also mean structure, intention, pattern that arises not randomly but with direction, even if we don't know the source of that direction. The idea that Earth is designed doesn't require a specific designer. It might mean something more abstract, like a universe governed by deep logic that just happens to yield life-supporting outcomes. Or it could mean something else entirely. There's also the possibility that Earth wasn't built from scratch, but selected. Out of many possible worlds, this one happened to support life. And so, here we are. But that raises another question. How many possible Earths are there? Are we just the lucky one in a trillion? Or is the universe teeming with other worlds like this, each with its own version of stability and strange beauty? We don't know yet, but as we start to discover exoplanets, and we've found thousands, we're beginning to see just how rare or common Earth-like conditions might be. So far, nothing quite matches what we have. We've found planets that are too hot, too cold, too big, too dense, too exposed to radiation, or too young. Planets without atmospheres, planets with too much gas. Planets that orbit stars that flare violently. The more we look, the more it becomes clear that Earth is unusual, not impossible, not singular, but certainly not average. And yet, average is hard to define in a universe this big. Maybe the rarity of Earth-like conditions is exactly what we'd expect in a system governed by chance. Or maybe it suggests something else. Either way, it invites us to keep asking. Another interesting point to consider is time. Not just space, not just location in the galaxy, but timing. Life didn't just need the right ingredients, it needed the right sequence. A stable planet, yes, but also billions of years of relatively calm cosmic weather. Not too many asteroid impacts, not too many solar flares, a moon to help stabilize, tectonic activity to recycle carbon, an atmosphere that gradually changed in exactly the ways life required. The timing had to line up. That's not impossible. But it's another piece in a growing puzzle. People have tried to explain this in many ways. Some see it as divine, others as luck, others as inevitable given enough time and space. But the idea that Earth might have been intentionally arranged, either directly or through some deep structure of natural laws, remains compelling. Not because it's provable, but because it continues to align with our lived experience. We are creatures who build things, who plan, who imagine outcomes before they happen. So when we look at a world that seems built just so, it's natural to wonder if something, or someone, planned it. Still, we have to be careful. Patterns can emerge from randomness. Perception can mislead. Just because something feels designed doesn't mean it is. Just because it's unlikely doesn't mean it was planned. But the flip side is also true. Just because science can explain how something happened doesn't mean we fully understand why it happened, or whether there's a deeper structure behind it. So the question we're exploring isn't about disproving science or proving belief. It's about holding a space where both can ask the same question from different angles. What if Earth was designed? What changes? What stays the same? And what, if anything, does that mean for how we live, how we see each other, and how we move forward? As we continue, we'll start looking at specific aspects of Earth that often come up in this conversation. The orbital sweet spot, the moon's uncanny role, the surprising balance of the atmosphere, the strange details of DNA, the many systems that had to align for intelligent life to emerge. Each of these opens up its own set of questions, not only about science, but about what we expect from reality itself. When we ask whether Earth was designed, we're not just wondering about planets or physics. We're brushing up against something deeper. This question, underneath all its science and speculation, is actually very personal. It's about how we understand our place in the universe, whether we think life is an accident that just happened to work out, or something more deliberate, whether we see the world as a series of coincidences, or part of something that was meant to be exactly as it is. That's why this idea feels different from other scientific topics. If you ask how volcanoes form or why seasons change, it's interesting, but not emotional. But when you ask if Earth might have been made on purpose, you're stepping into a much older conversation, one that goes back long before telescopes or textbooks. You're asking a question people have been asking since they first looked up at the stars and wondered what all this is for. It's the kind of question that shows up in philosophy, in religion, in mythology. Stories about the Earth being shaped by hands or spirits, or voices that spoke the world into being. And while many of those stories conflict with each other in the details, they share something important. They reflect a human instinct, the urge to connect what is with what means, to turn facts into purpose. That instinct isn't something we should dismiss. It's easy to assume that science and meaning are separate, that one tells us how and the other tells us why, but the line isn't always so clean. The more we understand about how the universe works, the more we notice moments where structure and outcome seem to converge in ways that feel, for lack of a better word, guided. Take something as basic as carbon. Life on Earth, at its core, is built around this one element. Carbon forms the backbone of DNA, proteins, and all the complex chemistry that makes cells go. It's incredibly versatile. It bonds easily, it forms long chains, it creates stable molecules that can carry information and build structure. Without it, life as we know it simply wouldn't work. And when you look at how stars create elements, you realise that carbon itself is the product of a very narrow set of conditions. If the physics of fusion were just slightly different, slightly stronger or weaker, the universe might be full of hydrogen and helium, but no carbon. No carbon, no life, no us. That kind of coincidence makes people stop and think. Not because it proves anything, but because it shows how specific things had to be. And the more we learn about the laws of physics, the more it seems like a lot of these values, mass, charge, gravity, the strength of forces, had to be within very tight ranges for complex matter to exist at all. Not just life, but stars, planets, chemistry. That's sometimes called fine-tuning. And it raises a question that sits quietly behind so much of modern science. Why these numbers? Why this version of reality? There are ways to explain it. One is the multiverse, the idea that maybe there are countless universes, each with its own set of physical constants, and we just happen to be in the one where everything lines up. That could make sense. But we don't have any direct evidence for other universes. Not yet. And even if we did, that still wouldn't tell us why our universe exists the way it does. It just pushes the question back a step. Another idea is that maybe these values aren't selected at all. Maybe they're just built into some deeper structure we haven't found yet. But that's still a kind of mystery. Because either way, we're looking at a reality where things had to be a certain way, and they are. And then, inevitably, you arrive at the deeper version of the question. Not just why is the Earth the way it is, but why is anything the way it is? Why do the laws of physics exist at all? Why should there be a universe with rules and structure and patterns and matter? Why should there be something rather than nothing? That's a question no telescope can answer. And yet, we keep coming back to it. Now, it's important to say, science doesn't need purpose in order to work. You can study gravity without believing it was created. You can decode DNA without asking who wrote it. But science doesn't forbid those questions either. It just doesn't depend on them. And for some people, that leaves space for a kind of middle ground, a place where you can explore the world through evidence and still leave room for the possibility that there's more going on than we can measure. This is where design enters the conversation, not as a replacement for science, but as a perspective, a lens. It doesn't say that we should stop asking questions when something seems fine-tuned. It says the fine-tuning itself is worth noticing. And maybe, just maybe, it points to something deeper. Of course, not everyone agrees on what that deeper thing might be. Some people picture a conscious designer, a god, an architect, a being with intentions. Others imagine a kind of built-in intelligence to the universe itself. Not a person, but a process that naturally tends toward order, beauty, or complexity. Others see design as a human projection, something we impose on the world because we're wired to find patterns and stories. In each of these views, the question is the same, but the answers differ. Even so, the question stays. It sits there, quietly, behind everything we do. Every scientific discovery, every new image from a satellite, every equation or theory, all of it is framed by this strange fact, that we are here, looking, that there's something to look at, and that it behaves in ways we can understand. Think about that for a moment. Not just that the world exists, but that it's intelligible, that we can measure it, predict it, explain it, that our brains, which evolved from ancient nervous systems designed to find food and avoid danger, can now model galaxies, build computers, and ask whether the universe has a purpose. Why should the mind of a species on a small rock in a remote corner of a galaxy be able to grasp the rules that govern space and time? Again, that doesn't prove anything, but it's odd. It makes you wonder whether our ability to understand the universe is itself part of some larger pattern. Whether the universe is not only structured, but structured in a way that invites understanding. That's not a claim, just a thought. In the end, these questions don't have to be threatening. They don't take anything away from science. If anything, they show how science can lead us right up to the edge of mystery, and then keep going. You don't need to answer every question in order for it to matter. Sometimes just holding the question is enough. And this one, this idea that maybe the world was built, arranged, or shaped in some way, is one of the oldest questions we have. But it's also one of the most modern, because now we have the tools to look more closely than ever, to explore the building blocks of matter, the forces of nature, the dynamics of life. And as we do, the question only deepens, not because we're running out of explanations, but because the explanations themselves are so detailed, so precise, and so delicately balanced that they make you pause. They make you think, is this all just what happened to work? Or is it what was meant to happen? We can't answer that fully. Not yet. Maybe not ever. But we can keep asking. We can keep following the structure, the order, the logic. Not to prove anything, but to understand, and maybe in the process get a little closer to what lies at the heart of it all. When we start looking closely at Earth itself, not just its place in the cosmos, but its surface, its systems, the everyday materials beneath our feet, we start to notice certain patterns. Some are geological, some are chemical, some are mathematical, and some are structural. And the more we zoom in, the more those patterns can start to feel oddly intentional. It starts with the basics. The planet's crust, for instance, is divided into plates. These plates float on a hotter, softer mantle layer, shifting over time. This movement creates mountains, earthquakes, volcanoes, and even oceans. Without plate tectonics, the Earth's surface would likely be flat and static. Erosion would wear it down. Nutrients wouldn't cycle. Life, as we know it, might never have flourished. The movement of the plates also plays a role in regulating carbon. When volcanoes erupt, they release CO2. When mountains weather, they draw CO2 back down. That balance affects the climate, which in turn shapes the entire biosphere. Now that's a process science has mapped out in great detail. But when you look at it from a wider angle, it's hard not to wonder how many ways that system could have failed. The planet didn't just need a solid crust. It needed one that cracked, floated, and moved. If the crust had been too thick, or the mantle too stiff, the plates wouldn't shift. If it had been too active, the surface might be constantly remade, leaving no time for life to stabilise. Somehow, Earth landed in the middle. Not too calm, not too chaotic. The more we look at how things are arranged, the more this middle ground idea comes up. Soil, for example, is a mixture of minerals, organic matter, water, and air. But the ratio has to be just right. Too much sand, and water drains too quickly. Too much clay, and roots can't breathe. The best soils, the ones that grow forests, crops, and ecosystems, strike a careful balance. That balance can vary by region, but it's always within a narrow band of properties. Plants evolve to match those conditions, or maybe the other way around. That's a theme that comes up a lot. Coevolution. Not just plants and soil, but insects and flowers, fungi and trees, bacteria and animals. Systems that don't just work, but work together, each part shaped by the presence of the other. And sometimes the fit is so exact that it starts to feel more like assembly than adaptation. Consider something as ordinary as a seed. It contains everything it needs to grow, the instructions, the energy, the structure. It waits in the soil, responding to moisture, temperature, and light. When those conditions line up, it transforms. Roots stretch downward, stems reach upward. It's a process we can describe in biological terms, but the timing, sensitivity, and precision involved are striking. Even the shape of seeds, the way they travel, stick, sink, or float seems optimized. Not perfectly, but very effectively. It's easy to see all of that as the result of natural selection. Traits that worked survived. Traits that didn't faded away. But selection works on what's available. It doesn't build from scratch. It repurposes, adjusts, trims. So the starting materials matter. And when we look at those starting materials, the building blocks of life, carbon, nitrogen, oxygen, hydrogen, they're not just common, they're unusually versatile. They bond easily. They store energy well. They form the right kinds of molecules, the kinds that loop and twist and replicate. Some of that may be chemistry, but chemistry too follows rules. And those rules, in our universe, seem to lean toward complexity. That doesn't mean complexity is inevitable, but it does mean that once it starts, it has room to grow. And Earth, for whatever reason, seems to have given it a head start. Take water. It's not a metal or a gas or a particularly rare compound. But it has a list of unusual properties. It expands when it freezes, which means ice floats, a rare trait that allows life to survive under frozen lakes. It has a high specific heat, which stabilizes temperature. It dissolves more substances than almost any other liquid, making it the perfect medium for chemical reactions. All of those traits just happen to be ideal for life, and all of them come from the angle between two hydrogen atoms and an oxygen atom. If that angle was slightly different, water would behave completely differently, and so would everything that depends on it. Then there's the idea of fractals, patterns that repeat at different scales. You see them in river networks, mountain ranges, coastlines, tree branches, blood vessels. These aren't just pretty shapes, they're efficient. They move resources across large areas with minimal material. Trees send nutrients from roots to leaves using fractal branching. Our lungs do the same with air. These forms aren't random. They follow specific mathematical rules. Rules that keep showing up independently in different systems. Some call that convergence. Others see something more deliberate. Another example is the Fibonacci sequence. The spiral pattern found in shells, pine cones, sunflowers, galaxies. It's not universal, but it's common. And it often shows up where growth is involved. That's because it allows for efficient packing and expansion. Again, there's a mathematical reason behind it. But the fact that math shows up in biology at all is worth thinking about. That living things, shaped by blind processes over millions of years, often align with principles we find elegant or logical. It raises an odd question. Does the universe follow math because it has to? Or does math describe it so well because both come from the same source? That's not just a philosophical puzzle. It has real implications for how we understand structure. Because if life arises from patterns, and those patterns follow rules, then where do the rules come from? This is where the idea of blueprints comes in. Not in the literal sense of someone drawing up schematics, but in the sense of consistent systems that create outcomes. The Earth isn't random, and it isn't purely chaotic. There's order here, a kind of layered functionality. From soil chemistry to planetary motion, things behave in regular, testable, repeatable ways. That's what science depends on. But it's also what makes people wonder whether that regularity points to something behind it. Patterns can come from chaos. That's true. We've seen it in simulations and models. But those patterns often require very specific initial conditions. Tweak them slightly, and the outcome changes completely. Which makes you wonder, what were the initial conditions here? Why these laws? Why this structure? Why a world where minerals form crystals, plants respond to light, and animals can evolve eyes? That's not to say anything supernatural is going on. But the more we examine the structure of Earth, the blueprints in its soil, its systems, its cycles, the more the question keeps coming back. Could this have been arranged? Not by magic or miracle, but by a process we don't yet understand. One that includes design, not as a product of choice, but as a principle. A natural tendency towards systems that support life. We don't have to decide that now. We're not here to answer, only to notice. And what we're noticing is that Earth is not a random mix of stuff. It's a deeply interconnected system, full of rules, balances and alignments that seem to lean towards stability, growth and resilience. That doesn't mean it's perfect, far from it, but it works, and it works in ways that feel oddly tuned. When people talk about why life exists on Earth and not on Mars or Venus, they often mention something called the Goldilocks zone. It's a nickname for the area around a star where temperatures are just right, not too hot, not too cold, for liquid water to exist. And since water seems to be necessary for all known forms of life, the assumption is that any planet sitting comfortably in this zone has at least a fighting chance. Earth sits right in the middle of that range, close enough to the sun to avoid freezing, far enough to avoid boiling. The sun itself is stable and long-lived, giving the planet billions of years to develop complex ecosystems. It's easy to hear that and feel a kind of satisfaction, like the universe played a very specific game of darts and landed right on the bullseye. But as usual, the closer you look, the more complex it gets. The habitable zone isn't fixed. It depends on the size and brightness of the star. A smaller, dimmer star has a tighter, closer in Goldilocks zone. A larger, hotter star pushes the zone farther out. That might sound like a wash, but each case brings its own complications. Smaller stars tend to flare, sending out blasts of radiation that can strip away a planet's atmosphere. Bigger stars burn through their fuel faster, meaning less time for life to evolve. Earth's sun, it turns out, is just about average, stable, bright, and long-lived. It may not be the only kind of star that can support life, but it's one of the better ones. Then there's the orbit. Earth doesn't just sit at the right distance, it stays there. Its path around the sun is nearly circular. That means the amount of solar energy it receives doesn't vary wildly throughout the year. Some variation is useful, that's what gives us seasons. But too much would make the climate swing between extremes. A slightly more elliptical orbit could have made the planet uninhabitable in large regions. And yet, here we are, with a wobble that's not too sharp and a tilt that's just enough to stir things up without throwing everything off. Still, distance and orbit are just the beginning. A planet can sit in the habitable zone and still be completely sterile. Just look at Mars. It's in the outer edge of the Goldilocks range. It has ice. It may have had water in the past, but it's dry now and cold and exposed to radiation. The reason? Its magnetic field collapsed, and with it, much of its atmosphere was lost. No shield, no pressure, no warmth, no protection. The ingredients were there, but the kitchen fell apart. Venus is on the other end, just inside the inner edge of the habitable zone. It's about the same size as Earth and has a similar composition, but its atmosphere is thick with carbon dioxide, creating a runaway greenhouse effect. Surface temperatures are high enough to melt lead. Its clouds are made of sulfuric acid. If Earth is a warm cup of tea, Venus is a boiling kettle that never stops screaming. This puts Earth in a very small window, not just in terms of distance, but in how its systems work together. Its atmosphere is thick enough to trap some heat, but not too much. It contains oxygen, nitrogen, and carbon dioxide in just the right mix. Its oceans moderate the climate. Its weather systems distribute heat around the globe. The greenhouse effect exists but doesn't run out of control. For now, it's not a delicate balance exactly, more like a dynamic one. Things shift, adjust, compensate. When something changes, other parts respond. That flexibility is part of what makes the system stable. But again, it didn't have to be this way. Small differences in early conditions could have led to a planet that looked very different. And if you rewind far enough, you get to the formation of the solar system itself, the swirling cloud of gas and dust that gave birth to the sun and its planets. In that cloud, where Earth ended up was determined by a mix of gravitational pulls, collisions, and leftover materials. It could have formed farther out, where it would be a frozen rock. It could have formed closer in, where it might have ended up like Mercury. But it didn't. It formed here, in the zone where water could stay liquid, and life had the time and conditions to begin. Some see that as chance, the result of many rolls of the cosmic dice, and that's a valid perspective. But others look at the outcome. A planet with just the right temperatures, just the right chemistry, just the right history, and wonder whether the dice were loaded. Not in a rigged or unfair way, but in a way that suggests direction. Maybe not intentional, but not indifferent either. That line of thinking leads to more questions. Is the Goldilocks zone a unique feature or a common one? Do other stars have planets in the right range? As it turns out, yes, at least in theory. Thousands of exoplanets have been found, and quite a few lie in their star's habitable zone. But we don't know much about them yet. We don't know if they have atmospheres, water, or magnetic fields. We don't know if their climates are stable or violent. We don't know what's going on beneath the surface. And even if one of them has the right ingredients, we don't know if those ingredients have formed life, or if life ever got the chance. So Earth remains our best example, and the more we study it, the more finely tuned it seems. Not perfectly. Climate can shift, natural disasters can occur, ecosystems can collapse, but overall the balance holds. Life persists, and not just simple life. Complex life, conscious life, life that asks questions about how it all came to be. The phrase "just right" can sound simple, but it isn't. It includes hundreds of interacting systems, geology, weather, magnetism, chemistry, biology. all behaving in ways that support the presence and continuity of life. It's not just the location, it's everything the location allows. And still, that might not be enough to prove anything. Maybe it's a lucky outcome. Maybe life is rare but not impossible, and Earth is simply one case where things happen to line up. That's the standard scientific view. But there's also a quiet, persistent sense, not a conclusion, but a feeling, that this lining up goes beyond odds, that it reflects something deeper about how the universe works, or wants to work. If we assume design, what would that design be aiming for? Life, maybe, or complexity, or perhaps just balance, a system that holds itself together long enough to become interesting. That doesn't mean everything is good or easy. Earth isn't a utopia, but it is unusually well positioned for something rare and complicated to happen. Once you start looking beyond where Earth is, and start focusing on what Earth is, the structure of the planet itself becomes part of the story. Not just the surface, or the land masses we walk on, but the full layout, from its iron core to the shape of its orbit. If Earth was meant to support life, you'd expect that structure to be part of the plan. And even if it wasn't designed in any purposeful way, the arrangement of its parts still raises some interesting questions. A lot of this starts at the centre. Earth's core is made mostly of iron and nickel, and it's divided into two parts, a solid inner core and a liquid outer core. The movement of that outer core is responsible for creating Earth's magnetic field, which shields the surface from solar and cosmic radiation. Without it, the planet would be constantly bombarded by charged particles that could strip away the atmosphere, damage DNA, and make life a lot harder, if not impossible. That magnetic field doesn't just exist. It's generated through a process called the geodynamo. The Earth's rotation causes the liquid metal to swirl, and those movements generate electric currents, which in turn create the magnetic field. For that system to work, a few things have to be in place. You need the right materials. You need a certain amount of internal heat, which comes from radioactive decay and leftover energy from the planet's formation. You need a certain size, because smaller planets cool too quickly. You also need rotation, but not too much. Earth spins once every 24 hours, which is fast enough to keep the core moving and stable enough not to cause chaos at the surface. It's easy to take that for granted, but change any of those pieces. Make the planet a little smaller, a little slower, a little less metallic, and the whole magnetic system could fail. That's what happened with Mars. It likely had a magnetic field early on, but it cooled too fast, the core stopped churning, and the shield disappeared. What followed was the slow loss of its atmosphere and surface water. Above the core is the mantle, which moves slowly over time, driving the tectonic plates on the surface. Those plates, as we talked about earlier, are crucial. They're involved in recycling minerals, shaping continents, building mountains, and regulating the carbon cycle, but they also require a certain amount of heat and a delicate balance between rigidity and movement. If the mantle were too soft, the crust would break apart constantly. Too stiff, and nothing would move at all. Earth seems to have landed on the right settings. It's dynamic, but not unstable. Over time, continents drift, collide, break apart, and reform. That movement changes climate, creates new environments, and helps isolate ecosystems, a key driver of biological diversity. It's also part of why so many different forms of life evolved in different regions. Without that movement, the planet's surface might be uniform and stagnant. Even the crust itself plays a role. It's thin compared to the rest of the planet. Just a few kilometres deep under the oceans, a bit thicker under the continents. But it's where all surface life exists. The composition of that crust is rich in the elements life needs. Carbon, phosphorus, sulfur, calcium, potassium. Those elements didn't all come from Earth's original materials. Many arrived during a phase called the Late Heavy Bombardment, when asteroids and comets delivered organic molecules, water, and other building blocks. That event could have gone very differently. Too many impacts, and the surface might never have cooled. Too few, and maybe the planet wouldn't have the ingredients life needed. Instead, Earth seems to have received just enough, a mix of rocky and icy objects that added to what was already there. Another moment where things didn't have to line up but somehow did. On the outside of all that is the atmosphere, which acts as both a barrier and a support system. It keeps the planet warm, protects it from smaller space debris, and contains the gases necessary for respiration and photosynthesis. But it didn't start out that way. The early atmosphere was likely full of carbon dioxide, methane, and ammonia, toxic to modern animals but useful for early microbes. Over time, photosynthetic organisms began producing oxygen, which eventually transformed the atmosphere into what we have today. That change, known as the Great Oxygenation Event, could have gone either way. Oxygen is reactive. It can be harmful in high concentrations, but in the right amounts it allows for complex metabolism, which in turn supports multicellular life. The fact that Earth systems didn't collapse under the strain of that shift is another example of how feedback loops, both positive and negative, kept things within a certain range. The balance between carbon dioxide and oxygen is still being managed by living systems. Forests, oceans and soil act as carbon sinks. Volcanic activity and respiration add gases back into the mix. The result isn't perfect equilibrium, but a system that self-adjusts, at least over long time periods. In that sense, Earth's surface is less like a machine and more like a living organism. Responsive, flexible, always adapting. And then there's water. Its distribution isn't even, but it's effective. About 70% of the surface is covered in oceans, which help regulate temperature and circulate nutrients. Fresh water exists in rivers, lakes, ice, and underground aquifers. That mix supports both marine and terrestrial life, and it relies on a planetary system of rainfall, evaporation, and flow that's tied to both geography and solar energy. Even the tilt of the planet, about 23.5 degrees, shapes how sunlight hits different regions, creating seasonal cycles. That tilt is stabilised by the moon, which we'll look at in more detail next. Without it, the tilt might wobble chaotically, causing wild shifts in climate over short periods. Instead, we get a reliable rhythm that life has adapted to. Migrations, hibernations, flowering times, all timed to the angle of sunlight and the arc of the year. Pull all these pieces together, and what you get isn't a simple object in space, but a complex layered system. One that generates its own magnetic field, regulates its own temperature, cycles its own resources and hosts its own life. A planet that builds the conditions it needs and maintains them through feedback and flow. None of that proves anything beyond what we observe, but it opens up a different way of looking. Instead of seeing Earth as just a lucky combination of traits, you might start to see it as something with internal logic. Not logic imposed from outside necessarily, but logic that leads to life-supporting outcomes. Whether that logic was built in, or emerged over time, or exists as part of some wider framework, that's the question we're still circling. For something that hangs in the sky every night, the moon is a little strange. It's large compared to the planet it orbits. Its gravitational effect is strong enough to influence the oceans, and its role in Earth's stability is more than just a side effect. It might actually be one of the most important factors in why life has persisted here as long as it has. On the surface, the moon seems like a natural companion, a product of whatever forces shape the solar system. But when scientists started looking more closely, they realised its presence is harder to explain than it first appears. The leading theory is that the moon was formed by a massive collision. A Mars-sized object, often referred to as Theia, is believed to have slammed into the early Earth. The impact would have thrown huge amounts of material into orbit, which then gathered into what became the moon. This theory explains why the moon's composition is so similar to Earth's outer layers, and why its orbit is relatively close and stable. It also fits the models of how early solar system bodies formed and interacted. But this explanation depends on a very specific set of circumstances. The size of Theia had to be large enough to knock material into orbit, but not so large as to destroy Earth entirely. The angle of the impact had to be just right. A glancing blow, not a direct hit. The materials had to coalesce instead of scattering, and afterward, the system had to settle into a stable orbit that would last for billions of years. That's a narrow window. A little more speed, a slightly different trajectory, and the Earth might have ended up without a moon at all, or with a chaotic ring of debris, or with an unstable secondary body that eventually crashed back down. But that's not what happened. What we got instead was a single, large moon, one that rotates in sync with its orbit, always showing the same face to Earth, and orbiting at just the right distance to have meaningful effects without destabilizing the system. Those effects turn out to matter a lot. For one, the moon plays a critical role in stabilizing Earth's axial tilt. Without it, the planet's tilt could vary wildly over time, moving between near zero and extreme angles. That kind of variation would cause massive swings in climate. The seasons could become unpredictable, or even disappear. Regions that are temperate now could become frozen or overheated, and then shift back again. That kind of environmental instability would make it much harder for ecosystems to adapt and survive long term. The moon's gravitational pull also drives tides. Tides move nutrients in coastal ecosystems, help regulate temperatures in shallow waters, and may have played a role in the origin of life by creating wet-dry cycles that promoted chemical reactions. The ebb and flow of the oceans aren't just background motion. They shape coastlines, influence weather patterns, and affect the behaviour of countless species. There's also a subtle timing effect. The moon's influence on Earth's rotation is causing the planet to slow down very gradually. A few billion years ago, Earth's day was much shorter, around 6 hours. Over time, tidal friction has stretched that out to the 24 hours we know today. That process is still ongoing, though at a rate far too small to notice in a human lifetime. Still, the long-term result has been a slowing of the spin, which has probably contributed to the planet's climate stability. And then there's light. Not in a mystical sense, but a biological one. Many organisms use the moon's cycle as a clock, coordinating migration, reproduction, feeding, or sleep patterns. Coral reefs spawn in sync with moonlight. Insects navigate by it. Even some predators and prey adjust their activity based on how bright the night is. The moon creates a rhythm that many forms of life have built into their biology. All of this from an object that, by some estimates, shouldn't even be there. Statistically, large moons like Earth's are rare among rocky planets. Mars has 2 small irregular moons, probably captured asteroids. Mercury and Venus have none. In our current understanding of planet formation, large moons are not a guaranteed outcome. They're unusual. And yet, Earth has one. And not just any moon, but one that seems almost custom fit for the job. That's what keeps bringing this question up. Not because anyone thinks the moon was placed there with tools or blueprints, but because the outcome, a stable, life-supporting planet with a stabilizing satellite, is unusual enough to notice. The formation of the moon, its orbit, its effects, all of it adds another layer to the question of how Earth ended up with such specific properties. Some argue that if the moon hadn't formed, life might still have emerged in some form. That's possible. But complex multicellular life might have had a harder time surviving in a more chaotic climate, and the long-term evolution of intelligent organisms might have been far less likely without stable conditions. It's one thing to adapt to seasonal changes. It's another to deal with a tilt that swings wildly over tens of thousands of years. If you look at the moon purely as a random outcome, it's an impressive one. If you look at it as part of a larger structure, it's one more piece that fits surprisingly well. Either way, it's part of the system that makes Earth what it is. There are also more speculative ideas about the moon. Some suggest it may have helped protect Earth from asteroid impacts by altering the path of incoming objects. Others think its presence may have affected the distribution of heat within Earth's core, influencing the geodynamo that powers the magnetic field. These theories are harder to prove, but they point to a growing awareness that the Moon is not just a passive companion, it's an active part of Earth's history. And even now it continues to move, slowly drifting away from Earth at about 4 centimetres per year. That change is tiny on a human scale, but over geological time it adds up. A few billion years from now, total solar eclipses, where the Moon perfectly covers the Sun, won't happen anymore. The Moon will be too far away to appear the same size in the sky, which makes this current alignment, like so many things about Earth, part of a limited window. Not permanent, just long enough to matter. Most of the time, gravity doesn't get much attention. It's always there, always working, but almost always ignored. You don't notice it until something falls, or until you stand on a scale, or when your coffee tips over and reminds you that even invisible forces still win every time. But in terms of building a planet and keeping everything on it in place, gravity is more than just background. It's the structure beneath the structure. Gravity isn't a strong force, not by the standards of physics. Compared to electromagnetism or the nuclear forces, it's weak. A small magnet can lift a paperclip against the entire gravitational pull of the Earth. But what gravity lacks in strength, it makes up for in reach. It never shuts off, it never gets blocked, and it acts on everything with mass. That quiet persistence is what makes it such an effective organizer. Without gravity, Earth wouldn't be round. It wouldn't even be a planet. The matter that formed the Earth would still be drifting in a loose cloud, never compacting into anything solid. Planets form because gravity pulls together dust and gas over time, packing it tighter and tighter until pressure and heat force the material into a dense spherical shape. That same force pulled in the core, the mantle, the crust, not as random layers, but in an order that reflects their densities. Heavy elements like iron and nickel sank to the centre. Lighter materials floated upward. Gravity sorted the planet by weight, and that sorting still shapes how Earth functions. But gravity does more than shape Earth itself. It also keeps the Moon in orbit, pulls on the oceans to create tides, and locks Earth into a steady path around the Sun. Without it, the planet wouldn't just lose shape. It would lose everything holding it together. No orbit, no seasons, no protection from the harsh vacuum of space. The orbit in particular is worth pausing on. Earth's path around the Sun isn't random. It follows a stable, nearly circular route. That kind of orbit doesn't happen automatically. It's the result of balanced forces. The forward momentum of Earth's motion and the inward pull of the Sun's gravity. Too fast, and the planet would fly off into space. Too slow, and it would spiral inward. But Earth's speed and position work together in a way that keeps it locked in a near-perfect loop. A kind of falling that never finishes. That stability makes long-term climate patterns possible. It also provides a predictable framework for seasons, day length and energy from the Sun. Life adapts to cycles, and those cycles depend on gravity doing exactly what it does. It's not just the Sun that pulls on Earth. The Moon's gravity creates bulges in the oceans, which we experience as tides. The solid part of the Earth even shifts slightly in response, an effect called Earth tides. These tiny movements contribute to stress within the crust, which over long periods influences tectonic activity. In other words, gravity isn't just holding things together, it's shaping how they move and evolve. Even the tilt of Earth's axis, the angle that gives us seasons, is held steady in part by gravitational interactions. Without that stabilisation, the planet might tip more over time or spin chaotically. Instead, gravity from the Sun and Moon keeps the tilt within a narrow range. That's another way in which gravity supports a predictable environment. Not by fixing everything in place, but by creating limits within which variation can occur. At a smaller scale, gravity affects everything from mountain ranges to river flow. It pulls glaciers down slopes, guides rainfall into watersheds, and shapes erosion over time. The landscapes we see, valleys, cliffs, plains, are the result of material slowly moving under the influence of gravity. Even the way trees grow is shaped by gravity. Roots grow downward, stems push upward, guided by tiny cellular mechanisms that sense gravitational pull. All of these effects are easy to overlook because they happen slowly. Gravity doesn't make a sound, it doesn't flicker or glow, but its influence is continuous, and it connects every part of Earth's systems, from the rotation of the core to the position of clouds in the sky. Then there's the human side of things. Our own biology is tuned to Earth's gravity. The strength of our bones, the way blood circulates, even how we balance when we stand. All of it depends on a specific gravitational pull. In low gravity, muscles weaken, fluids shift, eyesight can change. That's why astronauts experience a range of effects in space. Their bodies are adapted to a specific force, 9.8 meters per second squared, and without it, everything has to adjust. If Earth had slightly more mass, gravity would be stronger. Bodies might need to be shorter or more robust. If gravity were weaker, the atmosphere might be thinner. It might even drift away over time. So the planet's size and mass aren't just abstract numbers. They're part of the conditions that make surface life possible. The atmosphere stays in place. Water flows the way it does. Humans and animals grow to certain sizes. Even birds and insects fly with wings that evolved under these exact conditions. And beyond Earth, gravity still acts as the main architect. It holds together galaxies, shapes the motion of stars, and bends light from distant objects. Something we've measured and used to detect things we can't even see directly. That bending of light, called gravitational lensing, is one of the ways we know dark matter exists. We can't see it, but we see its effects, just like we don't see gravity, but we feel its presence in everything that holds still or moves with direction. In a universe where so much seems chaotic or random, gravity is one of the few things that brings order, not in a perfect mechanical way, but in a quiet, persistent one. It doesn't explain everything, but it provides the conditions under which other things can happen, and without it, none of this would be here. Of all the substances that exist in the universe, water might seem like one of the simplest. 2 hydrogen atoms, 1 oxygen atom, that's all it takes. And yet, it behaves in ways that make it far more than just a chemical compound. On Earth, water is everywhere. It fills oceans, shapes weather, carves landscapes, and flows through every living cell. It's essential to life as we know it. But when you start looking at how it behaves, and how rare that behaviour is, it becomes harder to think of water as just a lucky coincidence. Water has a number of properties that make it unusual. One of the most important is its ability to exist in all 3 states, solid, liquid, and gas, within the range of temperatures found naturally on Earth. That's not common. Most substances tend to favour one state or require extreme conditions to change, but water can freeze, melt, and evaporate within a narrow range that aligns neatly with the planet's climate. That alone might not seem remarkable until you consider what those phase changes actually do. When water evaporates, it absorbs heat, helping to cool surfaces. When it condenses into clouds, it releases that heat, warming the atmosphere. This process plays a major role in distributing energy around the globe. It drives weather systems, helps regulate temperature, and keeps the climate from drifting too far in any one direction. Another key property is water's high specific heat. That means it can absorb a lot of energy before its temperature starts to change. This makes oceans and lakes into thermal buffers. They absorb heat in the summer and release it in the winter, smoothing out temperature swings that would otherwise be much more extreme. Without that buffering, the difference between night and day, or summer and winter, would be far more severe. But perhaps the most famous quirk of water is that it expands when it freezes. Most substances become denser as they get colder. Water does too, up until about 4 degrees Celsius. Then, as it approaches freezing, it begins to expand. The result is that ice floats. That single trait has enormous consequences. It means lakes and oceans freeze from the top down, creating an insulating layer that protects the water beneath. Life continues under the ice. Ecosystems survive the winter. And when the ice melts, it doesn't sink and disrupt everything below. Then there's the way water behaves as a solvent. It's sometimes called the universal solvent because it can dissolve more substances than any other liquid. That allows it to carry minerals, nutrients and gases through soil, rivers and living systems. Inside the body, water moves substances in and out of cells, transports hormones, regulates temperature, and helps maintain structure. Its polarity, the fact that it has a slightly positive side and a slightly negative side, allows it to form hydrogen bonds, which in turn affect how proteins fold, how DNA holds its shape, and how enzymes function. These traits aren't random. They come from the angle of the H2O molecule, the way electrons are distributed, and the nature of the bonds involved. Change those details even slightly, and water behaves differently, maybe less flexible, maybe less supportive of life. But here on Earth, water does exactly what it needs to do. What makes this more interesting is that water is actually pretty common in the universe. Hydrogen and oxygen are both abundant elements, and we've found evidence of water in many places, in the form of ice on moons and asteroids, as vapour in comets, and possibly as liquid under the surfaces of certain planets or moons. But what Earth seems to have, and what's much rarer, is water in large, stable, surface-level quantities. Oceans cover about 70% of Earth's surface. That's a huge amount, and they've been there for billions of years. No other planet in the solar system has anything comparable. Mars has ice and may have had liquid water in the past, but it's long gone from the surface. Venus may have once had oceans too, but its atmosphere changed and boiled them away. The fact that Earth's water stayed, that it didn't freeze entirely or evaporate, means the planet stayed within a narrow temperature window for a very long time. How Earth got all that water is still a subject of debate. One theory is that water was locked in the minerals that formed the planet and slowly released over time. Another is that it arrived later, delivered by icy comets or asteroids. It might be a mix of both. But either way, the amount and distribution of water ended up being just enough to create oceans, sustain weather, and support a hydrological cycle: evaporation, condensation, precipitation, runoff, that moves constantly between land, sky, and sea. That cycle supports ecosystems of all kinds. It nourishes forests, fills rivers, shapes coastlines, and wears down mountains. It erodes rock into soil and carries nutrients from one place to another. Without it, Earth wouldn't be the green, shifting, living planet we know. The land would dry out, plants would fail, food chains would collapse. Water isn't just an ingredient of life, it's the system that life moves through. Even its interaction with light plays a role. Water is transparent in the visible range, allowing sunlight to penetrate oceans and fuel photosynthesis in aquatic plants. If it were opaque, underwater ecosystems would have to survive in darkness, but they don't, because water lets in light, but not too much. It filters harmful ultraviolet rays while still allowing enough energy for life to thrive. Rain, snow, clouds, fog, all of these are parts of water's constant movement. They affect temperature, visibility, behaviour, even mood. They change how animals migrate, how people plant crops, how landscapes evolve. And the timing of those patterns, how often it rains, how long snow lasts when dry seasons begin, is linked to everything from geography to air currents to planetary tilt. Earth's climate and its water systems are locked into a feedback loop that, for now, continues to support a wide range of life forms. Even in the deep ocean, far from sunlight, life persists. Hydrothermal vents release heat and minerals, and entire ecosystems cluster around them. Bacteria convert chemical energy into food, supporting fish, crustaceans and strange organisms found nowhere else. These underwater environments are reminders that life doesn't always need light, but it still needs water. There's something striking about the fact that Earth's most common liquid is also its most vital. That a substance so simple in structure turns out to be complex in function, and that the conditions needed to keep it flowing, atmospheric pressure, surface temperature, planetary mass, are all tightly interwoven. This doesn't mean water was designed to behave this way. It may simply be that life adapted to what water already does. But even that explanation leaves open the question, why does water do all this in the first place? Why does a molecule with 3 atoms become the basis for a system that supports such a vast and varied web of living things? In a different universe, with different physics, water might not exist, or it might behave differently, or it might be irrelevant, replaced by some other medium. But in this universe, with these rules, and on this planet, water fits the role almost perfectly. It flows, carries, dissolves, freezes, and transforms, quietly running the background processes that life depends on every moment. When you start looking closely at the shapes that life takes, the way trees branch, shells curl, petals align, or crystals form, you start to see patterns, not just resemblance, but repetition. Certain structures show up again and again across different scales and environments. Some are symmetrical, some are spiral, some fit ratios that can be described with simple numbers. And while all of these forms can be explained by physical processes, the consistency is hard to ignore. Symmetry is probably the easiest one to spot. It shows up in faces, bodies, leaves, insects, snowflakes. When both sides of something mirror each other, whether vertically, horizontally, or rotationally, we call it symmetrical. That kind of balance can be structural, helping an organism move more efficiently or distribute weight evenly. But symmetry also seems to appeal to perception. Human brains are wired to recognize it quickly. We tend to find symmetrical faces more attractive. We use symmetry in design, architecture, and symbols. It registers as orderly, familiar, complete. In nature, symmetry often serves a purpose. A butterfly's wings match because they form together. A starfish has radial symmetry that helps it move and respond to its environment. Leaves grow in matched pairs to capture light evenly. Even many viruses are built with symmetrical protein shells, not because they need to be beautiful, but because symmetry is efficient. It allows for repeated use of the same genetic instructions. From a material standpoint, it's a shortcut. Make one piece, then copy it over and over. But not everything is mirrored. Some of the most interesting structures in nature are spiral. You see spirals in snail shells, hurricanes, whirlpools, and galaxies. You see them in pine cones and sunflower heads, in fingerprints and animal horns. Spirals often appear where growth is involved. They allow structures to expand outward while staying compact. As the organism adds material, a new scale, a new layer, a new petal, the spiral makes room without disrupting the whole. Many of these spirals follow a mathematical pattern called the Fibonacci sequence. It's a series of numbers where each new number is the sum of the two before it. 0, 1, 1, 2, 3, 5, 8, 13, and so on. This sequence shows up in how petals are arranged, how tree branches split, how seeds are packed. The ratio between Fibonacci numbers approaches what's known as the golden ratio, a proportion that seems to recur in both nature and art. It's not universal, but it's common enough that it invites attention. These patterns don't require any intelligence to appear. They can emerge naturally through processes of growth and competition. For example, if a plant is growing new leaves and trying to minimize how much each one blocks the sunlight for the others, it may evolve a spiral arrangement. That arrangement, in turn, aligns with the golden angle, a fraction of a full rotation that distributes elements efficiently. No one designed it to be beautiful. It just works, and yet it ends up being beautiful anyway. That's where the idea of sacred geometry often comes in. It's a term that's been used in different ways, sometimes spiritual, sometimes symbolic, sometimes just poetic, to describe patterns that seem to carry meaning because of their structure. Circles, triangles, spirals, hexagons. These shapes show up in religious art, in ancient architecture, in mandalas and monuments. But they also show up in snowflakes, honeycombs, and coral reefs. The overlap between natural geometry and human expression isn't accidental. It's possible that we copy what we see. We repeat these shapes in our buildings and symbols because they're already familiar from the natural world. Or maybe we're wired to notice them, to feel that certain forms are more complete, more meaningful, more pleasing. Because they follow simple rules we can sense, even if we don't consciously understand them. Hexagons are a good example. Bees build their hives with them because it's the most efficient way to divide a surface into equal areas with minimal material. It creates a strong, stable structure using the least amount of wax. But you also see hexagons in basalt rock formations, like the Giant's Causeway, or in bubbles that settle into foam. The same shape emerges from pressure and physics, even when no bees are involved. Crystals are another case. Their atoms arrange themselves into repeating patterns that can form cubes, prisms, or even complex branching forms. These shapes aren't carved or placed, as they grow that way. The structure comes from the internal rules of how the molecules interact. Temperature, pressure, and chemical bonds guide the growth, and the result is something that looks both random and deliberate at the same time. You also see fractals, patterns that repeat at different scales. Tree branches split into smaller branches, rivers divide into tributaries, lightning forks, veins spread, lungs divide. Each level looks like a smaller version of the whole. Fractals are efficient ways to distribute energy or resources. They allow a system to reach many points from a central core, and they often emerge from simple rules applied repeatedly. That's what makes so many of these patterns compelling. They don't require complexity to appear. They arise from feedback loops, constraints, and repeated processes. They're built into how materials behave under certain conditions. But even if they're not the result of intention, they look intentional. They create a kind of visual logic, something that seems too consistent to be meaningless. There's also a sense of harmony in how these patterns fit together. The way branches fill space without overlapping, the way spirals pack seeds with no gaps, the way snowflakes grow along symmetrical paths. These aren't chaotic outcomes, they're structured, and when you stack up enough structured outcomes, you start to wonder whether structure itself might be part of the deeper picture. Some scientists have suggested that certain forms, like spheres, spirals, or hexagons, are preferred solutions in physical systems. That is, given enough time and freedom, matter will tend toward these shapes because they're stable or efficient. That's a useful explanation, but it still invites the question, why are the stable, efficient solutions also the ones we find everywhere? Why do they happen to support life? Why do they appear in both cells and stars? There's no need to assume anything mystical to notice the patterns, but it's worth asking why the rules of the universe produce outcomes that feel both functional and aesthetically consistent. Why shapes that help plants grow also show up in our sense of art and beauty. Why the most effective structures are also the ones that recur most frequently. This doesn't suggest a blueprint in the strict sense, no written plan, no design document, but it might suggest a framework, a set of principles that guide what's possible, what's likely, and what's sustainable. Whether that framework comes from physics or mathematics or something more abstract, it's clearly embedded in how matter organises itself, and it's part of what makes the living world feel so interconnected. Looking at the outer forms of life, it's easy to be impressed by how well everything seems to fit together. But when you go inside, into the cell, the nucleus, the molecules that run everything, that sense of fit doesn't go away. If anything, it becomes sharper. The internal systems of biology are precise, layered, and full of interlocking parts. They don't just function, they coordinate. And the deeper you go, the more it starts to feel like something more than just chemistry. At the core of all this is DNA, deoxyribonucleic acid, the molecule that stores genetic information. Every known living thing uses DNA, or its close cousin RNA, to carry the instructions for how to build and maintain itself. DNA isn't just a substance, it's a code. It's built from 4 types of molecules: adenine, thymine, cytosine and guanine, arranged in sequences that determine how proteins are made. Those proteins, in turn, run the machinery of life. It's often compared to a language, not just because it uses a limited alphabet, but because it has structure, syntax, meaning. A small change in a DNA sequence can alter a protein's shape and function, sometimes slightly, sometimes drastically. The same gene might be reused in different organisms, performing similar roles with small variations. And the way that information is read, copied and interpreted is so organized that it feels less like a chemical reaction and more like a process. When you look at how DNA works, it's not just about storing information, it's about managing it. There are sequences that act like start and stop signs, signaling when a gene should be activated. There are regulatory genes that control other genes. There are repair systems that scan for errors during copying and correct them. And all of this happens inside a structure just a few micrometers across, in every cell, in every living thing. That level of organization raises questions, not because it's hard to imagine how it came to be, but because it's hard to ignore how effective it is. The standard explanation is evolution by natural selection. Small changes in genetic material create variation. The variations that improve survival get passed on. Over time, that leads to complexity. And the evidence for that process is strong. We can see it in fossils, in laboratory experiments, in the shared genetics of related species. But even within that framework, the mechanisms themselves stand out. Proteins fold into specific 3-dimensional shapes based on the interactions of their amino acids. That folding is essential to their function. If a protein folds incorrectly, it often can't do its job. And yet, inside living cells, that folding happens automatically, guided by the sequence of the amino acids and assisted by other molecules that act like chaperones. There's no conscious awareness in any of this, but the system works with a kind of elegance that's hard to dismiss. It's not random trial and error. It's thousands of moving parts working together in the right order at the right time. Consider enzymes, proteins that speed up chemical reactions. Without them, most of the reactions that keep organisms alive would happen too slowly to matter. But with them, those reactions happen millions of times faster. Enzymes are highly specific. Each one fits its target like a key in a lock. They're not just functional, they're selective. And life depends on that selectivity to control when and how things happen. Then there are molecular motors, tiny machines made of protein that move things around inside cells. Some of them walk along cellular structures, carrying cargo from one place to another. Others spin, pump, or open and close gates. They convert chemical energy into motion, often in ways that mirror mechanical devices at a much larger scale. None of these systems are unique to complex life. Bacteria have them. Plants have them. Every living thing is built from variations of the same tools. The parts are different, but the principles are shared. That consistency suggests a common origin, which supports the idea of evolution. But it also raises the question of where the original instructions came from. The first sequences, the first proteins, the first membranes. Abiogenesis, the origin of life from non-living matter, is an area of active research. Scientists have proposed various models for how the first self-replicating molecules might have formed under early Earth conditions. Some theories involve clay surfaces, deep-sea vents, or ice-covered lakes. There's progress, but no single explanation has been universally accepted. The challenge is that life requires more than just molecules. It requires systems that copy, regulate, respond, and evolve. And while it's possible that those systems emerge gradually from simpler forms, the transition between chemistry and biology remains one of the most difficult steps to model. That gap, the space between random molecules and functioning cells, is where some people start to wonder whether biology shows signs of engineering. Not necessarily in the way machines are designed by humans, but in the sense that the pieces seem unusually well suited to the roles they play. The code isn't just data, it's executable. It runs instructions, it modifies itself, it adapts in real time. Even the way genetic information is compacted into the nucleus shows this efficiency. Human DNA, if stretched out, would be about 2 meters long, yet it fits inside a microscopic space, wrapped around proteins, folded into loops, and organised so that the right genes can be accessed when needed. That's not chaos, that's management. And beyond DNA, cells contain multiple layers of feedback systems, signals that trigger growth, division, repair, or death. These systems keep organisms in balance. They respond to damage, stress, hunger, infection. They communicate with each other through chemical messages, adjusting based on conditions. It's not that mistakes don't happen, they do. But the system doesn't depend on perfection. It depends on resilience. Biology isn't flawless. Mutations can cause disease. Systems break down. But the fact that life continues despite constant disruption is itself a kind of engineering, not rigid but adaptive, not static but dynamic. This doesn't mean cells were designed by a conscious mind. It may be that the systems we see are the ones that survived because they work, and that's entirely plausible. But when you see the level of coordination involved, the natural comparison is not just to a factory or a city or a machine, but to a code base. A set of instructions that not only builds itself, but maintains and updates itself. And just like software, biology has layers. There's the raw code, the sequence of DNA. There's the operating system, the cellular machinery that interprets it. There are inputs and outputs, error correction, feedback loops. And there are networks, interactions between genes, proteins, cells, and organs that create behaviours, responses, even thoughts. So the question shifts. Maybe it's not, was biology engineered, but can engineering and biology be thought of in the same terms? Is the comparison just metaphorical? Or does the structure of life suggest a deeper connection between systems that emerge through evolution and systems that are built intentionally? That's still open. But the deeper we look into life's code, the more structured it seems. Not random, not improvised, but layered, regulated, and deeply integrated. Once you understand that DNA acts like a code, it becomes harder not to see it as a kind of language. It doesn't use words or grammar in the way spoken languages do, but it has its own rules, its own alphabet, syntax, structure, and meaning. It's written in a 4-letter chemical script, and it contains instructions not just for building proteins, but for when and where and how those proteins should be made. It's information stored physically, instructions embedded in matter. The question is whether that language was invented, discovered, or something in between. DNA isn't just a long chain of chemicals, it's organised into genes, which are sequences that can be transcribed and translated into proteins. But those genes are only part of the story. There are also regulatory regions, sequences that tell the cell when to start and stop reading a gene, how much of a protein to make, or what conditions should trigger a change. There are enhancers and silencers, sequences that influence genes from a distance. There are introns, which are parts of a gene that get cut out before the final product is made. And there are non-coding regions, sometimes called junk DNA, though that term is slowly disappearing, that may play roles in structuring the genome or influencing how it's expressed. All of this behaves less like raw code and more like a programming language, one that includes not just instructions but context, one that supports layering and conditional behaviour. In computers, code gets compiled and executed. In cells, DNA is transcribed and translated. Both processes require a system that knows how to interpret a set of symbols. Both rely on precision, structure, and timing, and both can break down when the rules aren't followed. But DNA doesn't sit there being read all at once. Only a small fraction of it is active at any given time. Different genes are turned on in different cell types, at different stages of development, in response to different signals. The same DNA sequence can lead to very different outcomes, depending on what part of the body it's in, or what environmental conditions are present. That flexibility is part of what makes complex life possible. And it's part of what makes DNA feel like more than just data. It behaves like a system. What's interesting is that this system appears to be universal. All known life on Earth uses the same basic genetic code. The same 4 letters, the same codon structure, the same translation rules. A codon is a set of 3 bases that codes for one amino acid. There are 64 possible codons, and only 20 standard amino acids, so the system has redundancy. Some codons are synonyms, others act as punctuation. Start here, stop here. But that whole system is shared by bacteria, plants, animals, everything. That suggests a common origin, some point in the deep past when life settled on one code and every branch of evolution carried it forward. But it also raises a question. Why that code? Why that structure? Scientists have explored whether the genetic code is optimized, whether it's the best possible arrangement of codons to minimize errors and support flexibility. Some studies suggest it's close to optimal, not perfect, but surprisingly efficient at reducing the effects of mutations and ensuring robustness. If that's true, then it could be that life didn't just adopt any code. It adopted one that works particularly well. Whether that means the code was selected naturally, or that certain structures were more likely to survive, depends on how you look at it. Either way, what we have now is a system that works across all forms of life and has continued to work, with variations, for billions of years. There's also the question of interpretation. Humans didn't invent DNA, but we did discover how to read it, how to translate chemical sequences into information. And when we did, we found something astonishing. Not just complexity, but logic. Not just molecules, but instructions. That discovery has led to entire fields of research: genetics, molecular biology, bioinformatics. We now manipulate DNA with tools like CRISPR, redesigning genes with increasing precision. We can synthesize sequences, insert them into cells, and watch them function. In some ways, we've started writing in the language of life. But we didn't create the language itself. It was already there. This is where the idea of design often re-enters the conversation. Not because DNA looks manufactured in the way a computer chip does, but because it behaves with purpose. It handles information in ways that resemble software, logic circuits, or carefully planned instructions. It's not random noise. It's structure with output, and it's embedded in every living thing. There's also the issue of meaning. In human languages, meaning comes from intention. Someone writes or speaks with a goal of conveying something. With DNA, the meaning isn't conscious, it's functional. A sequence has meaning because it causes something to happen. It builds a protein, triggers a reaction, allows a process to unfold. But does that kind of meaning carry the same weight? Is functional meaning enough to call it a language? Or is that just a metaphor we're borrowing from human systems? That's part of what makes this area so ambiguous. The metaphors work because the systems are similar, but the interpretation depends on what you're looking for. You can see DNA as the result of evolutionary trial and error, where sequences that work are kept and refined. Or you can see it as a system so tightly tuned that it suggests forethought, not necessarily a conscious designer, but maybe a deeper structure behind the way life organizes itself. There are even efforts to design entirely new genetic codes. Alternative base pairs, synthetic amino acids, new rules of translation. So far, these experiments show that other systems could work in theory. But that only highlights how remarkable the natural one is. It's efficient, it's resilient. And it supports an enormous range of biological outcomes, all built on the same basic script. Whether DNA was discovered or designed may come down to what you mean by those words. It wasn't designed by people, and it wasn't discovered in the way math or physics might be. There's something eternal and abstract. It's a structure that seems to emerge naturally from the rules of chemistry and the dynamics of evolution. But the fact that it works so well and in such consistent ways makes it feel like it has properties we usually associate with engineered systems. That doesn't prove anything. But it does shift the conversation from wondering how life began to noticing that life behaves as if it's built on a kind of deep grammar, one we didn't invent, one we're still learning how to read. Living things can't survive without a protective barrier, not just physically but chemically, a membrane that separates inside from outside. At the scale of cells, that's the cell wall. At the scale of the planet, it's the atmosphere. But unlike the walls of a container, Earth's atmosphere isn't static. It changes, moves, responds, and regulates. It's not alive in itself, but it acts as part of the living system. It holds everything in, but it also lets just enough out. The atmosphere is made up mostly of nitrogen, about 78%, followed by oxygen, argon, carbon dioxide, and trace gases. That mix may seem ordinary, but it's anything but. Change the ratio slightly and the system stops working. Too much oxygen and wildfires become uncontrollable. Too little and animals suffocate. Without nitrogen, plants can't grow. Without carbon dioxide, photosynthesis stops. The percentages aren't symbolic. They're functional. They maintain the chemistry that life depends on. The balance didn't appear all at once. Early Earth had a different atmosphere, full of volcanic gases like methane, carbon dioxide, sulfur compounds. It was toxic by modern standards, but not sterile. Microorganisms evolved in it, and eventually some of them began to release oxygen through photosynthesis. That oxygen reacted with iron in the oceans, forming rust that sank to the seafloor. For a long time, oxygen levels stayed low. Then they began to climb, slowly, then rapidly. That change, called the Great Oxygenation Event, transformed the atmosphere. Oxygen allowed for more efficient energy production inside cells. That made multicellular life possible, but it also caused extinctions. Organisms adapted to the old atmosphere couldn't survive in the new one. So the system reset. Life evolved again under the new rules, with new strategies. Oxygen didn't just enable complexity, it enforced it. Even now, the oxygen level is regulated, not by a machine, but by feedback between ecosystems, geology, and climate. Plants and algae produce it. Animals consume it. Fires reduce it. Weathering of rocks locks away carbon. Volcanoes release it. If one part moves too far in one direction, the others adjust. The result is not perfect stability, but bounded variation. It's a system that breathes, in cycles, in pulses, in feedback. One of the most noticeable aspects of the atmosphere is its pressure. At sea level, it presses down with a force of about 14.7 pounds per square inch. That pressure keeps water in liquid form, allows for efficient gas exchange in lungs, and supports everything from the boiling point of liquids to the structural strength of biological tissues. If it were much lower, water would evaporate too easily. If it were higher, respiration might not work the same way. The pressure supports the conditions for life, and life, in turn, maintains the gases that set the pressure. The composition of the atmosphere also determines how heat moves around the planet. Some gases absorb and re-radiate infrared energy. These are the greenhouse gases: carbon dioxide, methane, water vapour, and others. Without them, Earth would be cold and lifeless. But too many, and the planet overheats. The system is dynamic. Greenhouse gases come and go, but the range stays mostly within the limits where life can adapt. Then there's the ozone layer, a thin region of the atmosphere that absorbs most of the sun's ultraviolet radiation. UV light is dangerous to DNA. Without that protection, mutations increase, cells die, life becomes unsustainable. But with just enough ozone, harmful rays are blocked while beneficial light passes through. The ozone layer forms naturally from reactions involving oxygen and sunlight, but it can also be damaged by man-made chemicals. That vulnerability isn't a flaw, it's a sign that the system is sensitive, tuned to specific interactions, reliant on a steady input of energy and chemistry. The atmosphere also moves. Winds distribute heat, moisture and particles across the globe. Jet streams steer weather patterns. Ocean currents interact with air currents. Together they move energy from the equator to the poles, balancing temperature and shaping climate zones. Without this movement, the tropics would overheat, and the poles would freeze completely. With it, the planet remains livable across a wide range of latitudes. Then there's the hydrologic cycle, powered by evaporation, condensation and precipitation. Water vapour rises, forms clouds, then falls as rain or snow. That rain feeds rivers, recharges aquifers, grows forests. The atmosphere is the vehicle for that motion. It connects land, sea and sky. Not in a poetic sense, but in a chemical one. And it does so without needing central control. It works because of temperature, pressure, altitude, sunlight, physics, not planning. But the result looks like coordination. Atmospheric circulation also carries tiny particles, dust, pollen, microbes. Some of those particles affect cloud formation. Some carry nutrients across oceans. Some seed ecosystems in entirely new places. These aren't just side effects, they're transport mechanisms. They allow the biosphere to move, adapt, evolve. And through it all, the atmosphere remains just thick enough to matter. It extends about 100 kilometres up, but most of its mass is within the first 10 to 15. That narrow band contains everything we breathe, every cloud we see, every sound we hear. Beyond that, space begins. There's no sharp edge, just a slow thinning until there's nothing left. That thinness makes it fragile, but it also makes it functional. It allows sunlight through. It lets heat escape. It holds in just enough. This thin envelope is also what makes flight possible. Birds, insects, planes all rely on air pressure and lift. Even seeds and spores ride the air. The atmosphere isn't just a shield. It's a medium, a space where motion happens. And yet, despite all of this, the atmosphere doesn't call attention to itself. It's easy to forget that every breath is a product of planetary systems, that the oxygen in your lungs might have come from an Amazon tree or an ocean microbe, that the air around you is not just empty space, but the result of billions of years of feedback, adaptation, chemistry and motion. It's not that the atmosphere is conscious, but its behaviour suggests structure, not random drift, but cycles, not stasis, but equilibrium, the kind of regulation that hints at a system with constraints, thresholds, memory. Even if the materials are right, even if the chemistry works, timing still matters. Not just in seconds or hours, but across vast scales, seasons, cycles, ages. On Earth, things don't just happen. They happen at intervals, at rhythms. Some fast, some slow, some measured in the slow ticking of geological time. There's nothing mechanical about these cycles, yet they act like a clock, not built, but real. And it's that timing that keeps everything functioning. Earth rotates once every 24 hours. That rotation gives us day and night. It sets the pace for sleep, activity, photosynthesis. Every living thing, from insects to trees to people, has internal mechanisms that sync with that pattern. Circadian rhythms, hormonal cycles, flowering and feeding times. These are not just responses to light. They're programs shaped by millions of years of repetition. The planet turns, and life turns with it. The year too is fixed. One orbit around the Sun takes about 365.25 days. That motion, combined with the planet's axial tilt, creates the seasons. They're not just cosmetic. They shape migrations, trigger breeding cycles, regulate growth. Bears hibernate, birds fly, crops ripen. Even microorganisms time their behaviour to seasonal cues. That kind of coordination wouldn't be possible without consistent orbital timing. And the orbit itself is unusually stable. Earth's path around the Sun is nearly circular, with just enough eccentricity to cause variation in solar input without causing extremes. Some planets have more elliptical orbits, which leads to hotter summers and colder winters. Earth's near-constant distance from the Sun keeps solar energy within a range that supports life year-round, even with seasonal shifts. But the planet's motion includes more than just rotation and orbit. There's precession, a slow wobble in the axis like a spinning top that takes about 26,000 years to complete. There's also obliquity, changes in the tilt angle itself, and variations in orbital eccentricity over time. These cycles, known as Milankovitch cycles, influence long-term climate patterns. Ice ages, glacial advances, shifts in rainfall. They're all tied to these deeper rhythms. The timing isn't perfect, it's probabilistic, but it's regular enough to shape history. Even the Moon participates. Its orbit affects tides, of course, but also the length of the day. Over billions of years, the Moon's gravitational pull has been slowing Earth's rotation. The days are getting longer, a few milliseconds per century. That's slow, but it adds up. 1 billion years ago, a day was closer to 18 hours. That matters for biology. It affects how long organisms can photosynthesize, how internal clocks sync, how heat builds and dissipates. Evolution didn't happen in a fixed frame. It adapted to a moving one. Other cycles run in parallel. Solar activity follows an 11-year pattern, with peaks and dips in sunspot numbers and solar radiation. That activity affects Earth's magnetic field, influences satellite systems, and possibly plays a role in subtle climate shifts. Geological cycles unfold over tens or hundreds of millions of years. The movement of tectonic plates, the opening and closing of ocean basins, the rise and fall of mountain ranges, even mass extinctions show a kind of periodicity, though the causes are still debated. Then there's biology itself. Inside every cell, molecular clocks run continuously, measuring time with proteins that rise and fall in repeating loops. These loops aren't just reactions, they're mechanisms that anticipate. The cell doesn't just respond to light, it expects it. Genes turn on and off at certain times of day. Repair systems activate when damage is most likely. Behaviour isn't just reactive, it's timed. In humans, internal clocks regulate sleep, body temperature, hormone release, digestion. Jet lag is what happens when the internal time gets out of sync with the external one. Health problems can emerge when those rhythms are disrupted. The body needs consistency, not rigidity, but pattern. And that pattern comes from Earth's motion. Even reproduction follows cycles. Menstrual periods, gestation times, mating seasons, all linked, directly or indirectly, to light and time. Some of those links are clear. Others are buried deep in evolutionary history, shaped by ancient timing mechanisms that no longer serve obvious functions, but still tick in the background. And beyond biology, there's cultural time. Humans created calendars to track the sun and the moon. Agricultural systems depend on planting and harvesting at the right time. Religious rituals align with solstices, equinoxes, lunar phases. Our entire concept of timekeeping, seconds, hours, years, is built around Earth's movements. We carry watches on our wrists, but they're just miniaturized versions of cosmic rhythms. None of this implies control. The Earth doesn't know it's turning. The sun doesn't track its position. The moon doesn't count the tides. But the outcomes show up as consistency, as repetition, as rhythm. Not because someone set it that way, but because it stayed that way, long enough for life to notice. And once life noticed, it built those rhythms into itself. What stands out is how these rhythms layer. The fast cycles, day and night, rest on slower ones. Seasons, years, orbital variations. And those rest on deeper cycles still. The shifting of continents, the rise of mountain chains, the aging of stars. Each layer affects the ones above it. Together they form a kind of scaffolding, not imposed from outside, but emerging from interaction, movement, inertia. That scaffolding creates windows of opportunity, times when certain conditions line up: warmth, light, moisture, stability, and new forms of life emerge. Other times, it creates pressure, ice, drought, competition, change. Life adapts to both, but it needs time to do it, and Earth's regularity gives it that time. There's a difference between predictability and purpose. The fact that a clock keeps time doesn't mean someone needs to be watching it, but it does mean you can build on it. Earth, as it turns out, is buildable. Life, weather, chemistry, culture, all layered on top of consistent timing, and none of it works if the pace slips too far off course. There are parts of biology that feel like they came together one improvement at a time. You can trace them, small changes, small advantages, slow shifts over generations. But then there are features that seem to leap ahead. Not because they're unexplainable, but because they work so well it's hard to imagine how they ever worked partially. The human eye is one of those. It's often pointed to as an example of complexity, a system with many parts, each dependent on the others. Light enters through a clear cornea. The iris adjusts to control brightness. The lens focuses the image. The retina converts photons into electrical signals. Those signals travel along the optic nerve to the brain, where the image is constructed. Not passively received, but actively interpreted. Every second, the eyes take in millions of inputs and sort them into motion: colour, contrast, distance, threat, comfort. What makes this more interesting is that the eye isn't just a light sensor, it's a dynamic optical system. The lens adjusts shape for near or far vision. The pupils widen or shrink in response to both light and emotional state. Tiny muscles track objects, stabilize the field of view, and coordinate with head and body movements. The eye doesn't work alone. It's embedded in a system of coordination and prediction. And it's not just the hardware. The brain adds layers of processing: edge detection, colour correction, pattern recognition. It fills in blind spots. It stabilises the world even while the head is moving. It interprets what's seen based on memory, expectation and context. Vision is an interaction, not a direct recording. The usual explanation is evolutionary. Eyes developed from light-sensitive patches on early organisms. Over time, these patches became deeper, formed lenses, added muscles, refined focus. You can find versions of this process in nature today, from simple photoreceptors in jellyfish to complex compound eyes in insects to sophisticated vertebrate eyes like ours. Each step brings a survival advantage, even if the system isn't yet complete. That explanation holds up under study, but what's notable is how far the eye has developed, not just in humans, but in other animals too. Birds of prey can see UV light and detect movement at great distances. Some shrimp can see polarized light and detect colours we can't imagine. Cats and owls can function in near darkness. Squid have camera-like eyes structured differently from ours, but reaching similar functionality. These aren't weak, approximate versions of vision. They're tuned systems, fast, responsive, high resolution, and the eye is just one example. Echolocation in bats and dolphins involves sending out high-frequency sound pulses and interpreting the reflections. It's a full three-dimensional mapping system, done in milliseconds, underwater or in flight. Electric fish use fields to detect objects in murky environments. Some insects see in ultraviolet or infrared. Some snakes sense heat from warm bodies. These systems don't just detect, they analyse. They work in real time. They interpret noise as structure. Even something as common as the human hand is an engineering marvel. Multiple bones, tendons, muscles, nerves, all coordinated to produce fine motion. The opposable thumb allows grip and manipulation. The fingertips can detect textures at a microscopic level. The coordination between vision and touch allows for precision that machines still struggle to match. Playing a musical instrument, typing on a keyboard, tying a knot, these aren't brute force movements. They're timed, tuned, and constantly adjusted. Some parts of the body regenerate, some self-repair, skin heals, bones knit, the liver can regrow after damage. Other parts don't repair as easily, neurons for example. But even there, the underlying design is efficient. The brain rewires, it forms new pathways, it compensates for damage. There's flexibility built into the system, not endless, but enough to survive. Then there's development. Every person begins as a single cell. That cell divides, differentiates, and organizes itself into tissues, organs, systems. The instructions for that process are embedded in the DNA, but the execution is three-dimensional, continuous, responsive. Cells signal to each other. They respond to gradients, concentrations, contact. The body isn't just assembled, it grows, from inside out, from simple to complex, while constantly checking, adjusting, and regulating. Certain processes are timed down to the hour, when organs form, when systems connect, when changes should happen. If the timing is off, development can fail, but most of the time, it doesn't. It proceeds with accuracy that rivals engineered systems. That accuracy doesn't guarantee perfection, but it allows for complexity to emerge reliably. You can find similar precision in less visible systems. The immune system detects and neutralizes threats based on memory and pattern recognition. The endocrine system adjusts energy levels, growth, stress response, reproduction. The cardiovascular system delivers oxygen and nutrients with incredible efficiency, adjusting flow on the fly, responding to movement, temperature, damage. All of these systems are made of cells. Each cell is a compartment with its own internal logistics. Membranes, organelles, transport channels, waste removal. The cell runs itself, follows instructions, adapts to signals, and repeats the process constantly, dividing, dying, renewing. There's no single feature that proves anything, and yet when you stack the systems together, vision, motion, balance, coordination, communication, what you get isn't just survival, it's ability, awareness, creativity, the capacity to interact with the world in detailed, responsive ways. From the outside, humans might seem fragile, soft, slow, dependent on tools, but biologically, the human body is both adaptable and precise. It can run long distances, recover from injury, learn languages, manipulate tools, raise children, coordinate memory with planning, balance emotions with reasoning. Those aren't secondary traits. They're central to how humans operate. None of this argues against natural processes. Evolution provides a clear mechanism: variation, selection, adaptation. But even within that framework, some traits seem unusually successful, tuned not just for function, but for range. The eye doesn't just see, it adapts to light and dark, tracks motion, focuses near and far. The ear doesn't just hear, it detects tone, direction, rhythm. The body doesn't just move, it climbs, swims, dances, writes. These aren't lucky breaks. They're systems built on systems, refined over time, interacting across scales. There's no need to call them intentional, but they work with a completeness that makes them stand out. And this leads to a larger question, not just about how individual systems work, but how they work together. Integration, coordination. What keeps all of these processes in sync, and what allows them to respond to an environment that never stops changing? Some things happen because they must. Gravity pulls, water flows downhill, metal rusts. These are regular, predictable, mechanical. But some events aren't like that. They're specific, contingent, and once-off. An asteroid strikes, a molecule mutates, a volcano erupts. We call those accidents, not because they're mistakes, but because they could have gone differently. They didn't have to happen the way they did, but what's striking is how often those accidents lead to outcomes that, in hindsight, seem almost coordinated. Take the asteroid that struck Earth about 66 million years ago. It hit near what is now the Yucatan Peninsula. The impact released more energy than 1 billion nuclear bombs. It vaporized rock, kicked up global firestorms, blacked out the sky, collapsed ecosystems, and it ended the age of the dinosaurs. That was not a slow evolutionary process. It was a reset. Fast, violent, and complete. But it also cleared the ecological space that allowed mammals to expand, diversify, and eventually dominate. Without that single event, human beings might never have arrived. That's one event. There are others. Roughly 2.5 billion years ago, Earth's atmosphere began to fill with oxygen. Not because of a cataclysm, but because single-celled organisms learned how to use sunlight to split water. Photosynthesis. The byproduct was oxygen, which built up slowly in the atmosphere and oceans. At first, it was toxic to existing life, but over time it enabled entirely new forms of metabolism. Higher energy yields, complex cells, eventually multicellular life. One biochemical innovation changed the entire trajectory of life on Earth, not by design, but by consequence. Around 600 million years ago, multicellular organisms began to evolve more rapidly. Nervous systems, eyes, skeletons. The fossil record shows an explosion of diversity in what's called the Cambrian period. Some of that may have been triggered by oxygen levels reaching a certain threshold. Some by genetic innovations like the rise of regulatory genes that control body plans. Whatever the cause, the timing was narrow. A few million years in either direction, and the environment might not have supported the outcome. Even plate tectonics, the slow drift of continents, shapes outcomes in ways that seem disproportionate to the motion. The movement of land masses over millions of years changes ocean currents, isolates species, opens migration routes, blocks others. It creates mountain ranges, which influence rainfall. It moves species together or apart, and in doing so, it sets the terms for natural selection. Who survives, who mixes, who dies out. The formation of the Moon, likely from a collision with a Mars-sized body, is another example. It was chaotic, high energy, and probably one of the rarest types of impacts. But the result was a stable moon that helps regulate Earth's tilt, tides, and rotational stability. Without it, climate patterns might shift too wildly for large ecosystems to hold together. None of these events were guaranteed. They weren't part of some schedule, but they had consequences far beyond their initial scope. Not just chain reactions, but turning points. Crossroads where one outcome reshaped what was even possible afterward. Biology, too, is full of what look like lucky breaks. The appearance of DNA as a stable information storage system, the rise of proteins with flexible functions, the emergence of eukaryotic cells, cells with internal compartments like nuclei and mitochondria. That last step likely came from one cell engulfing another, not to eat it, but to work with it. A merger, a fluke that became permanent. That symbiosis allowed for larger, more complex organisms. Then there's sexual reproduction, which mixes genes and increases variation, speeding up evolution. But requiring cooperation between individuals, or the evolution of consciousness, not just behaviour, but awareness, memory, planning, reflection. Not inevitable, not universal, but real, and linked to a network of prior developments, any one of which could have gone differently. Even the human brain, with its layers of function, motor control, pattern recognition, language, sits on top of biological history that began with simple responses to light or touch. Each layer required earlier systems to work. Neurons, then circuits, then coordination between regions. And at every stage, the conditions had to be right. Energy supply, protection, time to develop. Looking at all of this, one way to think about it is as a filter. Many planets may exist. Many may even have water, or heat, or the right chemistry. But to reach complexity, and then consciousness, and then civilization, a long list of things must line up. And not just in any order, in the right sequence, at the right intervals. The timing can't be off. Too soon, and the system fails. Too late, and the opportunity's gone. That doesn't make it planned. But it does make it rare. What's unsettling is how narrow some of those thresholds are. If the Earth was slightly close to the Sun, the oceans might boil. Slightly farther, and they might freeze. If gravity were weaker, the atmosphere might drift away. Stronger, and the planet might collapse into something uninhabitable. If the chemical properties of water were different, even slightly, cells might not hold together. If DNA didn't fold the way it does, replication would be unstable. If a meteor had hit 30 seconds earlier or later, the extinction pattern could have been different. When a system works, it's easy to overlook the dependencies. The supporting pieces vanish into the background. But when you break those pieces out and examine them, it becomes clear how much had to happen just to make the current version possible. Not perfect, but stable. Not ideal, but viable. The term fine-tuning often gets used here, but that implies intent. What's observable is precision, a convergence of variables that seems unusually compatible, not because each part is exceptional, but because their relationship is. Timing, chemistry, physics, events, all stacked in a way that leaves very little room for error. And yet the system holds, it evolves, it changes, it breaks and rebuilds, but it doesn't collapse. Earth's history is full of accidents, extinctions, collisions, reversals, shifts, and somehow those same events create new structures, more diversity, new pathways, higher complexity. It's not that the accidents are rare, it's that they keep resolving in ways that allow life to continue, sometimes narrowly, sometimes astonishingly. Long before telescopes, genetics, and data models, people looked at the world and asked where it came from. They saw the stars move across the sky. They watched storms, seasons, life, and death. And what they noticed most was regularity, patterns, cycles, things behaving in consistent ways, repeating across time. And when faced with regularity, the question that usually follows is, who or what made it that way? The earliest answers were personal. Gods, spirits, ancestors. Forces with names, intentions, and stories. In those systems, the world wasn't just a place. It was a creation. The mountains, the rivers, the sun and moon, even animals and people, all shaped by unseen beings who acted with purpose. Sometimes that purpose was benevolent, sometimes it was chaotic, but either way, it gave events meaning. A drought wasn't just weather, it was a message. A gift wasn't just luck, it was favour. Those ideas weren't random. They came from trying to understand something bigger than the individual, something that moved according to rules, but that also responded to behaviour. And while modern science has replaced those explanations with models built on observation and testable predictions, the core impulse, to look for agency behind structure, hasn't disappeared. It's just changed format. In ancient cultures, design was linked to divinity. A complex object implied a maker. A beautiful form implied intention. You see this in Greek philosophy, where some thinkers imagined a prime mover, a shaping mind. You see it in Eastern traditions, where the world is treated not as a product, but as an unfolding system, deeply ordered. And you see it in religious texts, stories where creation is deliberate, even personal. Later, with the rise of monotheism and formal theology, the idea of design took on new language, creation ex nihilo, purpose, divine will. The universe wasn't just shaped, it was chosen. It had a beginning, a goal, and a structure. That view held sway for centuries, not just in religious life, but in scientific thought as well. Early naturalists often saw their work as discovering the mind of God through the study of nature. Then, in the 19th century, Darwin offered a different model, one without foresight. Evolution by natural selection described how complex organisms could arise from simple beginnings through variation and filtering over time. It was a major shift, not because it denied design, but because it removed the need for it. You could explain biological order without invoking intention. That didn't answer all questions, but it changed the frame. Since then, science has moved further in that direction. The standard view now is that systems, whether biological, planetary or cosmic, can emerge from the interaction of rules, matter and time. Complexity from simplicity, not through construction, but through self-organisation. At each stage, the process is local. No central control, just feedback, selection and iteration. But even within that model, the sense of design persists. Not in the traditional sense, not a watchmaker in the sky, but in the structure of the outcomes. The brain behaves like a computer. The genome behaves like a script. The laws of physics behave like a programming interface. These analogies aren't perfect, but they're persistent. We keep finding systems that remind us of the systems we make. And lately, that loop has tightened. Because now we don't just describe biology with engineering terms. We build biological tools using engineering. We write genetic code. We simulate ecosystems. We evolve digital organisms inside algorithms. We build models that design other models. And in doing so, we start to see the line between natural design and artificial design blur. Artificial intelligence, once a speculative concept, now writes, paints, translates, predicts. It doesn't think the way people do, but it processes structure. It finds patterns, and sometimes it finds solutions that surprise even its creators. Algorithms evolve. Neural nets adjust. Complex behaviour emerges from simple rules. Sound familiar? This isn't to say that algorithms are divine, but they've forced a new question. Is design always conscious? Does order require a mind? Or just a set of conditions? If a machine can create something meaningful without understanding it, then maybe understanding isn't necessary for construction. And if nature can create structure without intention, then maybe intention isn't the only route to complexity. That's where the conversation has landed. Not between science and religion, but between different models of emergence. Some say the universe is self-organising, others say it was shaped. But both sides agree. The results are structured. That structure can be described, analysed, replicated, sometimes even predicted. And it runs deep, from physics to chemistry, from cells to consciousness. What's changed over time is how people talk about it. We no longer frame the world as built by hands. We talk about systems, about constraints, thresholds, probabilities. But the core idea, that function implies form and form implies cause, still drives much of the curiosity. It shows up in everything from simulation theory to the search for extraterrestrial intelligence. If something works too well, we look for a reason. The difference now is scale. Ancient explanations stayed on Earth. Gods of rain, gods of fertility, gods of war. Now the questions reach further out. Was the universe itself configured to support life? Do other configurations exist where life fails? Are we the result of random sorting, or are we in a scenario that favours observers because only observers can notice it? That idea, the anthropic principle, doesn't answer the question. It reframes it. If you're in a universe where life exists, it's no surprise to find yourself able to observe it. But that doesn't explain why the universe permits observers at all. And so the cycle continues. From gods to algorithms to simulation hypotheses, Every version of the question comes back to the same point. The outcomes look like something that works, not always perfectly, not always gently, but with a level of precision, integration and timing that resists easy dismissal. It started as metaphor. We described the brain as a machine, DNA as code, the cell as a factory. These comparisons weren't literal, but they helped explain things. They offered structure, a way to picture what couldn't be seen directly. But over time, the metaphors started to look less like illustrations and more like mirrors. As our digital systems grew more complex, they didn't just resemble biology. They began to behave like it. Simulations started small. A few rules, a few moving parts, a digital ant following a scent trail, a flock of virtual birds aligning in flight. But even in those early experiments, something interesting happened. Out of simple instructions came complex behaviour, not because it was programmed, but because the conditions allowed it. Interaction created emergence. That principle now powers everything from video game worlds to climate models. We feed in data, we define constraints, we press run. The system responds. Sometimes it surprises us, sometimes it fails, but more often than expected it behaves in ways that feel familiar. Populations rise and fall, cities form, languages evolve. Artificial agents develop strategies we didn't write, not because they understand, but because the math supports it. Simulations don't create real worlds, but they can approximate them. They let us see what might happen if a variable shifts. Temperature rises, genes mutate, resources deplete, and through that they've become more than tools. They've become thought experiments, not just what is, but what could be. And at a certain point, the gap between model and reality starts to narrow. You can now simulate evolution itself. Digital organisms with virtual genomes mutate, compete, adapt. They develop locomotion, sensory patterns, even cooperative behaviour. No one tells them how. They discover what works by trial. And because computers don't tire, these cycles run thousands of times faster than in nature. Evolution, compressed into hours. In some cases, the solutions they find are unfamiliar. Not optimal in a human sense. Not elegant, but effective. Algorithms don't look for beauty. They look for success under the rules they've been given. And sometimes the things they produce, shapes, sequences, strategies, echo patterns found in the natural world, spirals, branches, cycles, fractals, not copied, but rediscovered. That echo raises questions. If digital systems with minimal input tend towards certain forms, what does that say about those forms? Are they just efficient? Or is there something deeper, some underlying geometry that all systems, biological or artificial, fall into when given the chance? The simulation idea goes further. Some have proposed that our own universe might be a simulation, not figuratively, but literally. A digital environment running on a substrate we can't observe. The idea isn't science fiction anymore. It's a philosophical hypothesis, floated by physicists and computer scientists alike. If a civilization advanced far enough to simulate consciousness, the argument goes, there could be many more simulated realities than real ones, and statistically, we might be in one. There's no direct evidence for this. But there are oddities, limits in physics that look like resolution, discreteness in matter and energy, observations that collapse only when measured, boundaries that resemble computation more than continuum. These could just be features of the physical universe, or they could be artifacts, signs that the system we live in has edges, rules, shortcuts. Even if the simulation idea isn't true, it has utility. It forces a new perspective. If reality behaves like a system, we can study it like one. We can analyse its rules, map its parameters, search for consistency. We're not assuming purpose. We're acknowledging structure. Virtual reality adds another layer. We now create digital spaces so immersive that the brain begins to treat them as real. Games, training modules, design tools, all simulating environments that don't exist, yet still produce meaningful experience. In those spaces, perception becomes the main variable. If the brain accepts it, the difference between real and simulated begins to blur, and in those same systems we now place agents, artificial intelligences that learn, respond, adapt. These entities don't think like people, but they process information, they explore options. Some even begin to show behaviours that mimic learning, not in a conscious sense, but in a pattern-seeking one. It's not hard to imagine a near future where simulations run not just for prediction, but for exploration. A world where we generate new chemicals, test new medicines, evolve new designs, all inside digital frameworks, and where the systems that find those solutions weren't written line by line, but trained, shaped, guided by selection. That's where the boundary starts to break, between writing a program and raising a program, between architecture and emergence. It's not that this replaces the old questions, it reframes them. If reality can be simulated, even partially, then the distinction between design and discovery becomes thinner. Maybe design is what happens when conditions favour certain outcomes. Maybe discovery is just recognising what the structure already allows. Simulations don't have to be perfect, but if they produce systems that work, respond, adapt, then maybe they offer a kind of parallel creation, one we understand better, not by asking who built it, but by watching how it unfolds. If something looks structured, it's natural to ask if it was made that way. But the next question is harder. If it was designed, then why like this? Because this version of Earth is not perfect. It works, mostly. It sustains life, clearly, but it's also uneven, fragile, full of blind spots, trade-offs and strange choices. Bodies wear down, ecosystems collapse, natural disasters kill without warning. The same systems that enable growth also allow for suffering. If it's a design, it's not clean. And that raises the possibility that it's not design in the way people imagine it. The idea of a designed world usually comes with assumptions that things are made for a reason, that there's a best version, that problems are exceptions, but nature doesn't follow that logic. The most successful systems aren't the most elegant. They're the ones that survive long enough to matter, which often means the ones that are just good enough, not perfect, just stable. There are parts of Earth that feel like they were built to support life. The atmosphere, the tilt, the presence of water. But there are others that seem more indifferent. Earthquakes, viruses, genetic diseases, predators that evolve faster than prey. Prey that suffer without evolving at all. Extinctions that wipe out entire branches of life before they have a chance to adapt. These aren't flaws in a blueprint. They're features of an open-ended process. Even in the human body, so often described in terms of precision, there are structural compromises. The spine, inherited from creatures that walked on 4 legs, struggles with the demands of upright posture. The eye has a blind spot where the optic nerve exits the retina. The trachea and esophagus share a path leading to a constant risk of choking. The brain, for all its capabilities, is prone to distortion, addiction, delusion, degeneration. Evolution explains this. Structures adapt slowly, often through reuse. A solution that works gets copied and modified, not redesigned from scratch. That leads to inefficiencies, overlapping functions, unnecessary complexity, vestigial organs. But it also leads to flexibility. A design that's good enough doesn't need to be optimized. So if we're talking about design, maybe it's not the kind we're used to. Not planned in advance, not guided by a single objective. Maybe it's more like emergent architecture, shaped by constraints, feedback, accident. In that frame, why like this becomes, why does this version keep surviving? Which is a different kind of question. There's also the issue of scale. Some patterns only look messy from up close. Zoom out and the rough edges blend into structure. Climate systems fluctuate, but over long periods they stabilise. Ecosystems collapse, then reform around new species. Genetic diversity creates vulnerabilities, but it also creates resilience. Life, as a whole, has lasted billions of years. That's not a sign of perfection. It's a sign of durability, but it still leaves room for wonder and for discomfort. Because for all the systems that seem finely balanced, there are just as many that seem arbitrary. Why does reproduction rely on randomness? Why do beneficial mutations take so long to spread? Why are so many parts of nature locked in cycles of violent starvation competition? The answer, from a design perspective, might be that suffering isn't a flaw, it's part of the mechanism. Pressure drives adaptation. Scarcity drives cooperation. Failure drives novelty. But that explanation carries weight. It implies a kind of moral distance, a system that works by letting parts of itself break. Humans tend to imagine better versions, a world without pain, without aging, without extinction. A body that repairs itself fully, a planet without tsunamis or drought. In those imagined worlds, the question flips. If Earth was designed, why wasn't it made more like those? The response might be that trade-offs are inevitable, that complexity requires risk, that evolution, or any self-modifying system, can't be tightly controlled without losing the ability to grow. But that's speculation. It assumes goals, and the patterns we see don't clearly point to one. They point to survival, not direction. In technology, humans design systems toward specific ends: speed, efficiency, safety. But nature doesn't optimize in those terms. It adapts for what works under pressure. That means some things are elegant, others are awkward. Some parts are ancient, others are improvised. The brain is powerful but also vulnerable. The immune system is adaptive but also reactive. Intelligence allows for planning but also for anxiety. There's no consistent theme, no single idea that ties it all together. Just a history of forms that seem to build on what came before, without ever fully restarting. If there's design in that, it's not centralized, it's distributed, layered, maybe even unconscious. The idea that Earth was designed doesn't require it to be perfect, but the reality we see, full of beautiful systems that sometimes fail in brutal ways, suggests that if design is present, it's operating under different rules, not human logic, not human goals, possibly not even human values. It's also possible that we're asking the wrong question, that design and randomness aren't opposites, that structure can arise without being imposed, that feedback, replication and memory are enough to produce apparent intention. In that frame, why like this becomes less about meaning and more about consequence, not who chose this, but what made this sustainable. There's a point in every system, no matter how detailed, tested or well modelled, where explanation stops, not because there's nothing left to know, but because our tools have reached their limit. And when that point comes, something else moves in. Sometimes it's silence, sometimes it's questions, and sometimes it's belief. Science works by building boundaries, measurable, repeatable, observable. It deals with what can be tested. Gravity isn't a theory because someone believed in it. It's a theory because it predicts what will happen next. Same with thermodynamics, evolution, electromagnetism. The strength of science isn't in what it says about meaning. It's in how well it handles prediction. But people don't live only on prediction. They live on story, on purpose, on connection. And when those things can't be found in the equations, they're often found elsewhere, in frameworks that offer more than mechanisms, that speak in terms of why instead of how. For some, that's religion. For others, philosophy. And for many, it's a blend of the two. Tradition shaped by culture, family, language and history. Systems of thought that help explain not just how the world works, but what the world means. And those systems don't disappear when science advances. They evolve alongside it. Physics, at its edge, begins to resemble philosophy anyway. Quantum mechanics doesn't just describe particles, it describes probabilities, observation, uncertainty. General relativity doesn't just explain motion, it rewrites the shape of space and time. These are not intuitive ideas, they stretch human language, they resist visualization, but they're real, confirmed by experiment, embedded in technology, guiding our understanding of the universe. And yet, even these models break down. We don't have a single theory that unites gravity with quantum mechanics. We don't know what dark matter is. We don't know why the constants of nature have the values they do, why the charge of the electron or the strength of the nuclear force fits exactly into the pattern that allows atoms to exist. These aren't small gaps, they're fundamental. Into those gaps, people bring meaning. Some say the universe simply is. No deeper reason, no hidden message, just a structure that happened to work, a roll of the cosmic dice that came up livable. Others see intention, not in the details necessarily, but in the fact that anything exists at all, that laws hold, that minds emerge, that order repeats itself in ways that allow reflection. Neither view can be proven, and neither one has to be. They're not models in the scientific sense, they're lenses, ways of interpreting what science observes. What makes this space between science and faith interesting is how many of the same questions live in both. What is time? What is consciousness? What existed before the beginning? Where does order come from? These aren't spiritual questions by default, but they become spiritual when the answers turn into values, into identity, responsibility, purpose. Even belief in science requires a kind of trust. Not blind trust, but trust in method, in integrity, in the assumption that reality behaves consistently, that measurements matter, that cause and effect are more than illusion. These aren't beliefs in a supernatural sense, but they're still foundational. Science doesn't prove itself from the outside. It's a system that works because it assumes the world can be known. Faith, in its many forms, works differently. It doesn't require observation. It holds when evidence runs out. It offers story where data stops. That doesn't make it less real. It makes it suited to a different kind of question. For much of human history, science and faith weren't separated. Early scientists were often driven by religious motives to uncover the workings of creation, to see the hand of God in the laws of nature. It's only in the past few centuries that the two have been framed as opposites. In practice, most people don't live strictly in one or the other. They live in the blend, trusting science to describe how, while turning to other systems to ask why. The interesting part is where they overlap. When faith tries to make scientific claims, it often runs into conflict. But when it speaks in metaphor, mystery, or meaning, it fills spaces science doesn't reach. And when science enters those same spaces, speculating about multiverses, simulations, or the nature of consciousness, it starts to sound like belief itself. This isn't failure, it's boundary testing. A sign that curiosity continues even after the models end. Many physicists acknowledge this openly. They describe the laws of the universe as elegant, surprising, or beautiful. They talk about simplicity hidden under chaos, symmetry breaking into complexity. They use words like fine-tuned, not to imply a tuner, but to describe how narrow the window is between a dead universe and a living one. Others look at the same data and see randomness, an ocean of possible outcomes, with this one just happening to work. The anthropic principle, that we observe a life-supporting universe because only life-supporting universes produce observers, doesn't explain why, but it explains why us. Still, the question remains, is the precision we see a fact of nature, or a reflection of how we interpret it? Are we reading meaning into structure, or are we uncovering meaning that's already there? That's where belief steps in. Not to answer definitively, but to suggest, to imagine, to hold open the door. Not everything needs to be resolved. Some parts of life are lived better with questions still intact. which brings us close to the end, though not a conclusion. Because the final question isn't whether Earth was designed or by whom. It's how we live in it now with the systems we've inherited. The air, the water, the timing, the patterns. The chance to reflect, to imagine, to build. The question never really leaves. It just quiets down sometimes. In the middle of work, in the noise of cities, in the patterns of habit, it fades. But then something brings it back. A night sky, a fragile fossil, a perfectly timed event. And there it is again, hovering under the surface. Is all of this something we found, or something we were meant to find? Designed or discovered? Built or emerged? Those two ideas have different roots, but they often land in the same place, at the edge of what we can explain, looking out. If Earth is a design, then it is the most intricate one ever encountered. Every molecule positioned, every cycle balanced, every feedback loop delicately layered into the next. A system that sustains itself across billions of years, that recycles and reshapes, that allows not only for survival, but for understanding. That by itself would be a kind of miracle, not one of spectacle, but of quiet structure. And if Earth is not a design, if it was discovered by itself through the slow push and pull of physics and chemistry and time, then it is no less remarkable. Because what it discovered was itself, a planet that became aware, a process that looped back and saw the process, life that learned to ask. Either way, the result is the same. We are here, thinking, watching, wondering, making tools, making sense, making stories. We study cells, galaxies, equations ourselves. We map things not because we're told to, but because we need to know where we are. And we are here. Not just physically, not just on a rock orbiting a star, but fully here. Aware of the conditions that allowed awareness, able to reflect on what came before, and imagine what might come next. Whatever else that is, it's rare. And maybe that's enough to hold on to, even if the origin remains unsolved. Maybe the power isn't in knowing the answer. Maybe it's in being able to ask. Because the systems continue, with or without a final explanation. The rotation of the Earth, the pull of the moon, the breath of the atmosphere, the rise and fall of ecosystems, the ongoing dance of genes and memory and environment. The rules haven't changed, but now we see them, and seeing them doesn't require certainty. It just requires presence, attention, a willingness to accept that some things are structured and strange and stunning, not because they were made for us, but because we're able to see them at all. That might be design, that might be chance, but either way it's discovery, and it's still unfolding. Thanks for spending this time here. Not rushing, not reaching, just sitting with a question that doesn't need to be solved to be worth asking. Whether Earth was designed or discovered, whether these systems are intended or emergent, the world remains no less astonishing. And you, here now, listening, breathing, aware, are part of that system too. Sleep well or think long. There's no pressure either way. The planet will keep turning, the patterns will continue, and the questions, or the good ones, will still be here in the morning. Good night.